Wonderful. Okay. So go back to here, do my this. Okay. All right. I think we're in business now. Okay, people popping up. Before I get started, a quick announcement. So I have prepared a final homework and it was uploaded today. Actually, I didn't get a chance to upload yesterday. And it's going to be two type of problem. One is deflection calculation, and the other is going to be the column analysis. Okay. And I repeat, for the column, we're not doing design, we're doing analysis. Okay. So let's try to get this homework done maybe next week. And the deadline for the homework will be before the final exam. Let's just say that will be a Thursday before final exam midnight. Okay. So this way you have more time to work on homework, and we have like 1 or 3 days for the TA and myself to grade it and give you the final grades on it. All right. So a few of you haven't scheduled your exam before the final exam day, and I know two of you have talked to me already about it. Okay. Now, if you need to do that, you need to submit a request to the test room, okay, testing center, and then they will ask me to read and then send exam sheets to them. All right. So please do that today. Okay. So let's get everything set it up. Okay, so that's about the exam. Now, our last day of class will be Thursday. We'll finish the column and we'll open up an office hour Thursday, okay? And the same time, we'll post the previous exam problem, say later today, and you can take a look at it and we can go over them Thursday as well, okay? And last thing regarding the class is that for the review, or actually response of an evaluation, CET evaluation, I have right now the response rate approaching 30%. It's much better than before, but still much lower than I anticipated or expected. So please help me out here, okay? And if you have no criticism, just want to say your general feelings about these courses, that means you don't have any comments or anything, just help me fill it up, okay? So if anything good, I also need to see that so I know that what I can keep doing for the next semesters, okay? All right, so that's all there is to be announced. So with that, let's get back to the class, okay? So last class, what we have learned so far, we have learned to produce the axial force and moment diagram, right? So that's what we call the interaction diagram, okay? So what is this interaction diagram? So if I have a force exerted on the column, by the way, if you're not muted, please do so. So I don't have a feedback from you, okay, Xander. Okay, I might have to mute you, all right? So when we talk about this, when we have an axial force acting on a column, right? We know that usually this axial force is distance E away from the center line, okay? So that means if I have to draw envelope, failure envelope, right? Meaning my maximum stress is gonna be in compression for sure. And when my maximum stress equal to F prime C, which is this fellow right here, we're able to see a failure, right? So that means the whole failure line is going to be a linear line right here in the red curve showing up here, okay? And unfortunately, our materials is not elastic, right? So our practical failure line is not straight as shown here. It's actually not linear, all right? So excuse me for a second. Let me pop it back, meet student in here. And popping back again. Okay, so should be good. And now the actual failure envelope looks like nonlinear like this, right? And we talked about this last time. We say that there are several points. Matter of fact, there are 5 points that we need to be aware of. That is point A, B, C, D, E. How do we get those points, right? So essentially, we shift the strain in the section. Basically increase the bending curvature of the section, right? So you go from full compression, matter of fact, uniform compression, right? And then goes to the second stage where we'll have zero tension. Meaning in extreme fiber, there will be no tension, right? And then you keep going and have a so-called balanced failure, right? Balanced failure means that I have reached the yield strength of the concrete. I've reached the yield strength of the concrete. Then keep going, right? Once you keep going and realize that the strain in the fiber, tensile fiber, we reach the critical limit, right? Control limit. That is 0.005. And then we call it tension control limit. And keep going, right? And then going from D to E, we essentially increase the eccentricity to infinity. So that time we don't have any axial force dominating anymore. We basically have a lot of bending moment, right? So you see that the strain diagram has changed to a pattern like this, where I have most of my tensile strain at one side. And that tensile strain is very high value, right? Much higher than 0.05. So let me just make a differentiation so you know which is which, okay? So this is approaching to a very large number, okay? I wouldn't say infinity, but let's just say large number, okay? And we will talk about this, but we don't usually use strain to determine the stage E here, okay? Today I'm gonna show the example. You see that we basically utilize the eccentricity to determine stage E here, okay? But nevertheless, right, we have figured out this state, and let me pop back real quick to admit students here. Okay, that's Sophie and Kenneth. And we have shown that, right, to do an analysis on these 5 points, we have to rely on equilibrium. So equilibrium of the column dictates that the total external forces added has to equal to the internal force, right? So you know that in the internal system, we have the compression force from the concrete, compression force from the steel, and tensile force from the steel as well. And all these total force will equal to the axial force that exerted on the column. All right. And then in terms of bending moment, right, we have to sum the bending moment with respect to the center of the section, right? Center of the section. So we use the half H distance to representing the center of the axis, right? The distance between the centroid of each forces are listed here, and you multiply by each component, and you get this moment, right? You got this moment, and that is the total moment generated on the column. And folks, sorry, this is another student here, and come back here. And this is our axial force and moment analysis diagram, right? Analysis diagram. Okay, so here at the end of this small analysis done here, we basically summarize 2 equations, right? And these 2 equations, folks, you're gonna need it for your exam, right? You're gonna need it for your exam. So these are the 2 equations needed for the exam, right? So now, if I have these, right, so the axial force equal to CC, CS, TS, that is 0.85 prime CAB plus AS prime, FS prime minus 0.85 prime C, AS and FS. Okay, so one moment, I want you to pay attention to this equation. Let's just take a look at it, right? So 0.85 is constant, sure. F prime C is given, usually for KSI concrete, something like that, fine. B is given, that is the width of the column, right? The only thing that is not sure is A. Okay, we'll talk about this, all right? Then AS prime, that is total compressive reinforcement area, right? Area of total compressive reinforcement is given, right? And then FS prime, okay, unknown, right? And 0.85 F prime C given here, AS given here, FS tensile stress, unknown. Okay, so in the first equation, in terms of axial forces, there are 3 unknowns. The effective compressive zone A, compressive stress in the compression reinforcement Fs prime, and the tensile strain in the tensile reinforcement Fs. So how do we determine them based on the different points? Well, straightforward, right? So remember, we have the top compressive strain here, always equal to epsilon Cu, right? 0.003. And we also know that at different point, right, epsilon s equal to 0, 0.0207, this is B, and this is C, and D equal to 0.5, right? And E is just a large number, right? We'll talk about this. But essentially, using this strain diagram, we're able to get C and A equal to beta 1C, so we get A, and we also get compressive strain Fs prime from the diagram, and also we get Fs from the strain in the tensile reinforcement, right? So this tells us if I want to find out the Pn corresponding to a different point A, B, C, D, E, I need to find my strain diagram first at this point, and then plug the number in to get this number, right? To get this Pn here. Okay, so that is the strategy. Same thing goes along with the moment capacity Mn, right? So we have F prime CAB known, and A unknown, right? A unknown, right? So these are here, ds minus half H, everything is basically known, right? So these are the unknown, Fs prime, unknown. And do I have Fs? Yeah, Ts right here is As Fs, right? So Fs is unknown and Ds minus half H known, right? So once I label out these known parameters, now I just need to find out 1, 2, 3, 3 unknown, just like the unknowns in the axial forces. Okay, so this is the strategy. Okay, this is the strategy to do column analysis. All right, so given an example, right, I have a section look like this, and the section have a width of 12 inch and a height of 20 inches. And I have 4 number 9 bars that are being tied by the stirrups, and this give us a 2.5 of concrete cover in compression size and 2.5 inch of a concrete cover in the tension side, right? So matter of fact, when I draw this, I actually draw it wrong because you think of it, right? You think of it. What really happening is that my axial force is going out of plane in this direction, right? So in terms of compression and tension, these 2 bars should be in compression. So 2.5 inch should be labeled here, and these 2 bars will be tension. That is 2.5 inch here. Okay, apologize, and that was the mistake. That was the mistake from last lecture, and here correct it. Okay, here correct it. All right, so if this is ds prime and this is ds, we basically have most of the geometry locked down, right? Now the question is asking us for f prime c 4 ksi, fy equal to 60 ksi, I need to find out pn, mn, corresponding to the balance failure, right? That means point C, right? Immediately, you know that this is looking at a strain in steel of 0.00207, right? 207. And then question 2, pn, mn, along tension failure region, that means somewhere between C and E, meaning we need to find somewhere at E, right? We need to find point E, okay? And then we also need to find out region the D to E, right? What is D? D is the strain equal to 0.005, the tension control limit. Okay, so that's how we are going to find the answers to 1 and 2, right? 3 and 4 is basically find a point between A and C, region A and C, and critical load for axial forces, that is point A. So all these questions, 1, 2, 3, 4, and the different ways asking you to find out point A, point B, point C, point D, point E. All right, all of them. Basically is asking to find all of them. So in the exam, if you were to find solutions to all these type of problems, right, in a column analysis, you don't have to concern yourself a lot in terms of wording. Just find me A, B, C, D, E. When I say find me A, B, C, D, E, that is to find out their axial force capacity and moment capacity at each point, draw them on the force, axial force and moment diagram, and finish the curve like that, okay? And then again, the curve will be in terms of connected lines between these points, right? Connected lines between these points. Okay, so that is the problem, right? Okay, so let's cut to the chase, right? So first point, trying point C here, that is the balanced failure, right? So for the balanced failure, I look at the strain diagram, epsilon Cu equal to 0.003, and epsilon S, tensile strain of the reinforcement equal to 0.00207, right? So with that number, I can do my plugin, right? I can do my plugin. I find my C compressive zone, which is 10.3 inch, my A, which is 8.76 inch, that is effective compressive zone. Now FS, in this case, it is balanced failure. What does it mean? Means that it yields, right? It yields. So the strength is 60 KSI, all right? Now, the compressive side is Young's modulus ES multiplied by the compressive strain of the reinforcement. To find the compressive strain of the reinforcement, as we said previously, we utilize the similar triangle, right? Similar triangle. And then we find out that the compressive strain is this fellow right here in the bracket, all right? And then we'll plug the number in and get my stress in the compression that is 65.9 KSI, which badly or unfortunately is larger than the yield strength, which is 60 KSI, larger than the yield strength, which is 60 KSI. So what happens? What happens is that ACI says, when you have a compressive stress larger than the yield stress, please use the yield strength. Okay, so capped it at Fy equal to 60 KSI. So with that, I calculate my compression force CC equal to 357 kips. Okay, so that's where we left off last time. All right, so today let's continue, right? So the total compression force in steel then is AS prime multiplied Fs prime minus 0.85 F prime C. And I have this value to be 2" squared, y 2" squared. I have two number 9 bars in compression, right? 60 KSI, which is the yield strength of the compression side, has to be capped minus 0.85 multiplied by the concrete strength 4 KSI, right? You do this calculation, you find yourself at the position that the compression from the steel is 113.2 kips, okay? 113.2 kips, that is the compression from the steel. So with that, let's take a look at tension, right? Take a look at the tension. So tension equal to AS Fy, where AS is again two number 9s, 2" squared, Fy 60 KSI. So I have 120 kips in terms of tension. All right, so now I have all these tension, compression, and I'm happy, right? So Pn, which is axial force, equal to Cc plus Cs prime minus Ts. Okay, compression, compression, tension. Tension is negative, compression is positive. Okay, so now let's bring the number in 357 plus 113.2 minus 120. So I have a 350.2 kips of compression force. Right? Now in terms of moment, Mn would equal to what? Cc multiplied distance, right? What distance? Distance is half h minus what? Half a. Okay, Cs prime, right? And that is half h minus ds prime. Okay, minus or plus. Why is that? Because although they're in a different sign, right? So look at the section, right? Although I have my axial forces right here, so this is a line. So compression force of Cc go this way, Cs somewhere go this way, prime, and tension goes this way, Ts. Okay, but since the axis is right here in the middle of it, so both, if I look at from the side view, right? So this is x, right? X direction. Okay, and then this is a P, and this is Cc, and this is Cs prime, and this is Ts. Okay, if I'm summing moment with respect to x-axis, right? So everything is what? Moment in terms direction-wise, it is what? Clockwise, right? Clockwise. They're all in the same direction and positive. Okay, so this is positive sign here. So Ts multiplied distance, which is what? Half h minus, or actually the other way around, d minus half h. Okay, d minus half h. You say why, Bob? Look, d is this distance right here, where the edges of the section is at. Okay, and half h is this distance here, and distance between the tension force to the centroid is d minus half h. Okay, all right, so that is our equation, right? Just plug the number in. What is compression force? Cc 357, and that is in terms of kips. Half h, 20" of height, so give me 10" minus half a, 4.38" from previous calc, and take this one out, let me be more consistent, all right? And plus Cs prime, and that is 113.2 kips multiplied by a 10" minus 2.5", okay? That is ds prime. And plus ATS, 120 kips multiplied by 17.5", that is D, by the way, right? ds, you call it, right? Minus 10". Okay, so I have everything summarized, right? This is in terms of a kips inch. I want to convert it back to kip foot, right? So I need to divide a conversion factor of 12" per foot. Okay, so I end up with 310 kip foot. And that is my moment capacity Mn here. Moment capacity Mn here. All right, so at this point, I have my Pn, I have my Mn. So what I end up with is my eccentricity, E, equal to the moment divided by axial force. So I end up with 310 kip foot divided by 350.2 kips, okay? And that converted back to inch. So multiply inch, 12" per foot conversion factor, and equal to a 10.66". All right, so now that is point C, point C. So remind us again where the point C is at, right? So in our head, the axial force is here and the moment is here. So Pn and Mn, and the curves looks like this, right? So it has a belly right here, and that point here, folks, is my balanced point C. Balanced point C. Okay. Now, when I ask you guys to find out C, right? What I really meant is you draw the diagram, you label it, right? How to label it? This is basically axial force. So bending moment is right here first, right? So 310 kip foot as the first axis, right? This is coordinate. And then I have this number here to be 350.2 kips. Okay, and the eccentricity is 10.66 inch. So these are kind of like the coordinates for point C. So to be more specifically, this is Mn, this is Pn, this is E here. Equal, equal, equal. Okay, so now you have labeled point C on my diagram, Okay, all right. So before I continue, any questions so far on this, folks? Any question? Anything? All quiet? Are we good? Okay, just so you know, I'm recording this, okay? So you will be able to see it on YouTube, and please go back to take a look at the YouTube, okay? Just make sure you understand most of the content here. You will be tested on this fine, okay? All right, so that is point C. Now, next question. Basically, it was asking us to find a point, all right, between point E and point D, right? So between D and E, okay? And let me just say that if I want to find D and E, right, I essentially look at D, that is the strain in the steel equal to 0.005, right? And E, we don't know the strain, but we know that it is pretty large, very large number. So we're trying to be smart here. I say that, you know what, I am going just to find a point at the strain equal to 0.0075, okay? So to find that is not bad because the stress in the steel immediately I know it's going to be yielding stress. So 60 KSI for the FS. All right. And I look at my diagram, right? I look at my diagram. I say, look, the strain diagram dictates that I have a failure strain of epsilon Cu equal to 0.003. And I have a tensile strain somewhere here in the reinforcement level epsilon S equal to 0.0075. You say, why, Bob? Why you say 75? Well, I just picked this number. So it between 0.005 and something very large, right? We don't know, but something very large, as long as it's bigger than 0.005. All right. So anyhow, I have this strain diagram laid out right now. So I have compressive strain, tensile strain, and I know the distance, right? Between the top fiber to the central neutral axis is C. This is between the top fiber and the tensile strain is ds, right? So I can calculate my C here, right? So C, use a different color, immediately using the similar triangle equal to a 17.5, which is ds multiplied by the distance of strain, so epsilon Cu divided by epsilon Cu plus epsilon S, okay? So that is C equal to 17.5 inch multiply epsilon Cu 0.003, bottom here 0.003 plus given 0.0075. Okay, so with that, I calculate my compressive zone to be 5 inch. How convenient, right? 5 inch. Okay, with that, I see the effective compressive zone now is beta 1 C, right? Beta 1 is the coefficient, right? We know that for 4 KSI concrete, this is 0.85. So multiplied by 5 inch, I have a 4.25 inch of effective compressive zone A. And now with that, right, I look at my Fs prime here. So epsilon S prime here is the distance of ds prime, that is 2.5 inch, remember? So first thing first, I need to find an epsilon S prime, that is the compressive strain, right? Compressive strain in the steel, right? So that equal to C minus ds prime divided by C and multiplied by epsilon, what? Epsilon Cu. Okay, again, similar triangle, right? So 5 inch minus 2.5 inch divided by 5 inch multiplied by 0.003, I have my epsilon s prime equal to some number here. Okay, and I don't want to calculate this out because immediately I cared about is fs prime equal to the Young's modulus ES multiplied epsilon s prime. So I just bring this whole thing in, right? Bring this whole thing in. ES, Young's modulus, 29,000 KSI, and multiply this whole thing, and just be lined up, right? 2.5 inch divided by 5 inch, and multiply 0.003, and then I get my compressive stress equal to be 43.5 KSI. Now, folks, when you see this number, 43.5 KSI, you're okay, right? You start smiling, wow, I don't have to worry about the capping business because that is lower than the yield strength of the steel, okay, of the steel. All right, so with that, I'm pretty happy, right? I started doing my business of finding the total force, right? So CC, concrete, equal to 0.85 prime C, A, B, and that is 0.5 multiplied 4 KSI concrete. A is what? 4.25 inch, and that is A, and B is the width is 12 inch. So got this whole thing laid out to be 173 kips in terms of compression for the concrete. All right, so CS prime, which uses the equation AS prime multiplied Fs prime minus 0.85 F prime C. Don't forget, we dig the bar out and put the concrete back in. So you got to take this out, right? So this is 2 inch squared, 2 number 9 bars multiplied 43.5 KSI Fs prime. We just calculated here minus 0.85 minus 4 KSI of concrete strength. Okay, so you end up with CS prime of 80.2 kips. Okay, now the tension side is straightforward ASFY because it has yielded, right? So 2 inch squared multiplied 60 KSI, I end up 120 kips, right? End up with 120 kips. Okay, so with all these, right, I can start doing my axial forces. Pn would equal to Cc plus Cs prime minus Ts, which, you plug the number in, 173 plus 80 minus 120. I got 133 kips. And Mn equal to a Cc. Remember the long equation, half H minus half A plus Cs prime, half H minus ds prime plus Ts. Again, this is plus sign, okay? Don't forget, and ds minus half H. All right, so plug the number 173 multiplied by half H is 10 inches minus 4.25 inch divided by 2 plus a CS prime 80 kips multiplied by 10 inch minus 2.5 inch, okay? ds prime 2.5 plus Ts 120 and multiplied by ds, right? ds is 17.5 inch minus 10 inches. That is half H. The whole thing bracket out. And then I got, sorry, did I see bracket out? No, I don't have to bracket. Apologize. Should be 1 component, 2 component, 3 component. Okay, I'm good. All right, so now MM would equal to 100. Sorry, before I do that, right? I need to do this. Everything in terms of kips inch, I want to convert back to kip foot. So divided by 12 inch per foot. That's what the bracket is for. Now MN will do a 238 kip foot. Okay. All right, folks, let me get our friends in here and then go back here. So that is my axial force, Pn, and bending moment. All right. As usual, practice, right? So E, which is our eccentricity, equal to mm divided by Pn, and that is 238 kip foot divided by a Pn, that is 133 kip, no foot, okay? And I want to convert back to inches, so 12 inch foot, and that leaves me a 21.5 inch. Okay. Sorry? Anybody? I'm sorry, did anybody said anything just now? Okay, I don't know what happened. Okay, so let me see. Do you guys still see my screen? Folks?
Yes.
Yeah.
Okay, okay. All right, just want to make sure you guys still online, okay? So I'm running a little bit fast today, but I need to get the whole thing in number, okay, cleared out. All right, so just slow me down or interrupt if you couldn't follow or anything I say is ambiguous, okay? Now, eccentricity now, after calculations, 21.5 inch, right? Pretty fast calculation. I were, happy with it. I was just about to move on to the next question, right? But before I move on to the next question, I want you to have a sense, I want to have a feeling of this eccentricity here. What does it really mean? It means that, right? And draw my section again, remember? We're doing this abstract thing, but it is actually regarding to this section here. And remember, I have a 12-inch of width, a 20-inch of height, right? And looks pretty neat, right? Because, it's a nice rectangular section, right? And the neutral axis is right here, 10-inch, from the top. And now we know that, right? This is so-called x-axis. So the force is acting along y-axis, but it's outside the section now. Why? Look, we just calculated out the eccentricity is defined between the center line here to the axial force. And that, folks, is 21.5 inch. All right, that, folks, is 21.5 inch. So that means what? Means that the force is already out of the column. Okay, it's out of the column. Okay, so I just want you to get a sense of the eccentricity here. All right, and again, put on this perspective that this is PM and this is MM, right? And remember the failure curve. It looks like in a linear curve, I have a belly button right here and go back to this pure bending mode. So again, let me map out A, B, C, and D, and E. And where are we at? Where are we at, right? The point we're doing is right here, okay? This is the point. And this point here, I have a, cannot label it, right? Because I don't know the number. It's not a ABCD or anything like that. But I know the number here, right? Sorry, I know the number here is 238 kip foot, okay? 133 kips with an eccentricity of 21.5 inch. Okay, you see, that is where my point is at, between D and E, between D and E. Okay, so that's where we're gonna label it. That's where we're gonna label it. Okay, all right. So we find a point between D and E, you're happy now, right? So what's next step? Next step is that I ask you guys to find a point that between, and this is my mathematical sign, between here, A and B. Between A and B. Okay, so it means my next point, right? My next point, so this is 3, and now I have a way to label, right? This is 0.2, right? 0.2, 0.3, and 0.1 is just C here, right? So we already done that. Okay, so where this point is at, right? I haven't done it, so I'm just label it. Okay, where this point is at. So you look at this 0.3 here, right? It's between A and B, right? So A is pretty much just axial forces, right? Pretty much just axial forces. Okay, now I want to take a look at B here, right? Take a look at the B here. So I know that for B, the strain diagram, looks like this. It's zero tension, right? It's zero tension, right? Zero tension meaning what? There's no strain in the steel. Or if this depth here is D, right, that is where the steel is at, remember? That is where the steel is at. That means my compressive zone, again, is same, isn't it? So it means that at B, what really happening is that the compressive zone C is approximately equal to the depth of the section ds. Okay, that's what it is. That's what it is. All right, so what does it imply? What does it imply? It implies that, implies that if I have my point 3 is before B, after A, so take an analysis, right? Analyze string at 3 here. So if A is a full uniform compressive string, looks like this. And this is a horrible drawing, but this is A. And B is something like this, right? Something like this. Okay, so that is my C here. So apparently at B, my C approximately equal to ds. Is that right? ds. But if you really look at A here and imagine the section can extend infinitely, right? And this is going to be always a parallel line because this is pure axial loaded. Let me say this again, okay? If I were to imaginarily, okay, imagine if I were to extend the section, right, of A at point A, this distribution of strain will always be like this, right? Meaning there's going to be a parallel line and it never intersects. So if this is point B, and I were to find somewhere point 3 here, that just means what? It just means in point A, C compressive zone is much, much larger than the depth D. And in this case, C is approximately equal to ds. So I just need to find out the point that at 3, C is larger than point B, sorry, larger than ds. And that is the criteria, okay? All right, before continue, do I see anybody? Okay, everybody's still here, good. Okay, so that is what we mean, right? We just need to find a point that with a compressive zone that larger than the depth. And that's what we're gonna do. That's what we're gonna do. All right, so after doing analysis, we find out, okay, you were basically asking me to find a point that have a compressive zone C is larger than the depth. Easy, right? So look at the depth is ds equal to 17.5 inch. Okay, 17.5 inch. Again, if you're asking how to get this number, Bob, h minus 2.5 inch, okay? H is 20, right? So that's how I get this number. I just need to find a C that is greater than ds. So what numbers is able to do that, right? So we'll just say let C equal to 18 inch. And that is larger than 17.5 inch. Slightly larger, but that's fine, right? Serve the purpose. Okay, so based on that, I determine that compressive zone C equal to 18 inches. And I say A should equal to beta 1 C. And for 4 KSI concrete, that is 0.85 multiplied 18 inch. And I have here 15.3 inch. All right. Now, why do I need that, right? Why do I need that? Because, right, I want to take a look at this here. And now I know my C is slightly larger, right? What do you mean by slightly larger, right? It just means that, look, this is different, okay? It just means that I have some compressive strain in the steel now. Because point B is zero tension, right? Meaning zero strain in the tensile reinforcement. But here, at point 3 here, I have some strain in the tensile bar, okay? In the tensile bar. Okay, this is ds. All right, so just so you know, but here, top here, still 0.03. So that is what we're looking at, the strain diagram. Okay, but nevertheless, let's just carry on, right? So CC, concrete compression force equal to 0.85 multiplied by a 4 KSI concrete, and A, that is 15.3 inch, and B, that is 12 inch. So I have a number which is 624 kips. Okay. Now Fs prime, right? Fs prime equal to Es epsilon S prime, and Es is 29,000 KSI. Epsilon S prime, right? Epsilon S prime, epsilon S is right here, right? Right here, and that is epsilon S prime. So this distance right here is ds prime's 2.5 inch. Remember? So this fellow here equal to a 29,000 KSI multiplied by a strain, right? So remember here, C minus ds prime divided by C multiplied epsilon C. You remember the equation? Okay, so that is the strain. So Fs prime equal to a 29,000 KSI that multiplied by C, which is 18 inch minus 2.5 inch divided by C, right? C is 18 inches again. C is now 15.3, okay? C is 18, all right? And you may ask, where you get the C again, Bob? I was given, okay? I assume that at the beginning, right? And multiply 0.03. So afterwards, I got my Fs prime equal to what? Some number, 75 KSI. When you see this number, you say, look, this is bigger than the yield strength of the steel. So I kept it at yield strength. Okay, we've done this before, so no surprise here, right? Typical. All right. Okay, so you're supposed to be happy about it, right? You're supposed to be happy about it, right? But now here is the problem. What is the problem? You remember this fellow here? No, that's not what I mean. This is what? This is Fs. This is Fs. Okay, that was supposed to be the tensile strain of the steel. All right, but when my compressive zone and my real compressive zone is, where the zero spring is happening, right? So my real compressive zone C here, when that is 18 inch and D is 17.5 inch, my tensile reinforcement just become compressive. What? Yes, you hear me right. Okay, you just heard me right. When you have a compressive zone C larger than the depth of the section, your tensile reinforcement just become compressive. Yes, so a wonderful division line dash here. So let's take a look at it. So Fs now equal to Es multiply epsilon s. Es 29,000 KSI, fine. Epsilon s, right? So that is epsilon Cu multiplied by ds minus C divided by C here. Okay, so inherited these numbers and plug them in. This one 0.003, this one ds 17.5 inch minus 18 inch divided by 18 inch, bracket out. Okay, what happened? What happened is that this thing become negative now. Trouble, trouble, trouble. Right? It was always positive and now become negative. Why it becomes negative? Because it become compressive. Because it become compressive. All right, but don't be alarmed, right? Let's carry the negative sign, right? Let's trust the system and see what we end up with, okay? So I carry the negative sign in it and do all the calculation, find out this is basically 2 KSI. Very small, but 2 KSI, okay? So that is the stress in the tensile bar, but the tension force equal to AS Fs. So AS is 2 inch squared, 2 number 9, multiplied by minus 2 KSI, so what? 4 kips. Okay, what does it mean? It means that I don't have a tension force anymore from the tensile reinforcement. The supposedly tensile reinforcement just cheated, right? Turned and becomes compressive reinforcement and becomes a contribution, a compression force of 4 kips. All right. You say, Bob, how does that reflect in terms of total compression, right? Pn. And this is how. So I have Cc, Cs prime, minus Ts, remember? Okay. So now Cc is 624 kips. Cs prime, that is 60 KSI, right? Multiply 2 inch squared, right? 2 number 9, and minus, bracket, minus 4 kips of Ts. Okay. So minus, minus, plus, right? So now I have a total axial force of 748 kips. Okay, 748 kips. Okay, so that's where the danger is at. Be careful with the sign system. Okay, all right. So Mn, easy, right? So 624. I spare you all the equation repetition again. Just use the number, and that is 10 inch minus 15.3 divided by 2 plus 120 multiply 10 inch minus 2.5 inch, right? This is basically Cc multiply half h minus half a, right? And plus Cs prime multiply half h minus ds prime. So happy. Now, what was before Ts, right? Ts is plus, remember? Ts and ds minus half H, right? Remember that, right? Was before that, right? So now these are equation, okay? Now this fellow here becomes what? TS become negative. Okay, negative 17.5 inch minus 10 inch. Okay. All right, so I just have a negative sign carry into the calculation. So my total moment just becomes 195 kip foot. 195 kip foot. All right, so eccentricity E equal to Mn over Pn, and that it gives me a 3.12 inch. Pretty small, right? Pretty small. So you look at the section again, right? Just want to see where it's at. Remember this beautiful section, right? And now this is x-axis, this is y-axis, and the P is right here. CL right here. Oh, sorry. Use a black line. So very close. Okay, so close that this distance right here is only 3.12 inch. All right, so that's what the eccentricity looks like. Okay, eccentricity looks like. All right, so to finish this, right? So I have Pn, remember, that's adding them up, right? Mn and the belly curve. Okay, and then A is right here, B is somewhere here. You notice sometimes I shifted B point quite a bit, okay? But that doesn't matter as long as it's in the number. So number 3 is right here. It has value of what? Let me just copy it down. 195 kip foot. Total force is what? 748 kips. And eccentricity 3.12 inch. And that is 0.3. Okay, that is 0.3. All right. Okay, so one more problem. Okay, I promise just one more minute. Okay, actually 4 minutes. Any questions so far? Yeah.
Yes. So did we find CS prime for that last question, number 3?
CS prime. Yes, we did here. Right. So how do we find it? FS prime right here, right? That is 75 KSI bigger than 60. We take it as 60, right? So CS prime equal to what? Equal to what?
I thought it was AS prime at times
prime, right?
Yeah.
So that is how much of reinforcement in compression? 2 number, 9 bars, right? So 2 inch square, right? And 60 KSI, right? So that's 120 kips, and that's 120 kips right here. Do you see it?
Yeah, thank you.
Yeah, no problem. Okay, all right, so that is problem number 3, right? So now problem number 4. Okay, problem number 4 basically is asking for pure compression, and that is our point A here, right? So you look at it, point A here, and that is point 4, right, as well. So that shouldn't be too hard, isn't it? That should be too hard. You say, why, Bob? Why? It's just complicated every time you take a look at the strain and everything. But for A, remember, it's uniform. Okay, so it's the same as the short column. Oh, what is short column? I forgot. Well, short column is this. Remember, Pn equal to P naught, and that is 0.85 F prime C multiplied Ag minus AST, okay, and plus Fy AST. Long time ago we talked about this, okay? So no moment, right? Mn equal to 0, eccentricity equal to 0, right? So Pn essentially equal to 0.85 multiply 4 KSI of a concrete and multiply 12 inch, multiply 20 inch, that is the Ag, gross area, right? So BH, right? Minus 4 number 9 bars, 4 inch squared, plus yield strength of the bar, 60 KSI, and total reinforcement in what? In the column. AST is not tensile reinforcement, all right? AST is total reinforcement, because in pure axial or pure compression, there's no tensile reinforcement, right? Everything is in compression. Remember? Everything is in compression. All right, so once I have that, I mapped out Pn equal to 1042 kips. Pretty large number, right? So that means I look at the section here, right? So needless to say, my P is sitting right here in the center very nicely, right? Without any eccentricity equal to 0, right? So Pn looks like this, Mn look like this, the belly curve still stands, look like this, okay? And A or 4 is A here, and to label that out as 0, 0, okay? No moment, 1042 kips. And this is Pn, right? 0 again, because eccentricity equals 0. And that's how we label point 4 or point A. Okay, all right, I got 1 minute left. So let me summarize. So I got all these points mapped out. Okay, so now let's summarize. So in sum, right? So sum, right? I want to plug in all my numbers in the single diagram. All right, so I have a point right here mapped out. I have point 3 somewhere here between B and A. Okay, A is also point 4 here. And I have my C somewhere here, belly button right here. And this is, I believe, number 1, problem number 1. And I go back here, this is D, this is E, and this is my point number 2. Okay, I have all these. Oops, sorry, 1 second. Okay, so that is my curve. Okay, that is my total curve. Now to label my eccentricity, you have option. Okay, you can also do this. If this is my origin O, you do an error. You say this is E eccentricity equal to 0.
We can't see your screen.
You can't. All right, let me do that again. Okay. Okay, you guys see the screen now? Do you see the screen now?
Yes. Yes.
Okay, sorry about that. So E, I can represent as a big red arrow starting from 0, pointing to the point, label the number. So E equal to 0 for 0.4, E equal to 3.12 inch for 0.3, E equal to 10.66 inch for point B. Point C here, I even draw it around, apologize. Point C here, okay. 0.1 basically, E equal to 10.66 inches. And then for 2 right here, E equal to 21.5, I believe. All right, I think it's 21.5 inch. Okay, all right. So that's where we're at. And just for freebie, right? I threw in a freebie for E, although I didn't calculate, but immediately I know this is infinity, okay? By definition. Okay. All right, so we're done. That is how you solve the problem for column, okay? Axial force moment interaction diagram, okay? All right, we are done with all the column, but I will do one extra problem on Thursday. We'll continue on Thursday, okay? So I see you on Thursday. Please help me finish the review, okay? CET evaluation, all right? If I have something nice to say, please help me out as well, okay? All right, thank you very much. And I'll see you tomorrow. Bye now.
Professor, would you mind to upload the final exam from last year so that we can study for it? If
Yeah,
you
I
haven't
think
yet.
I think I mentioned in the beginning of class, I'm gonna do it today.
Okay, awesome.
Yeah,
Thank you.
not a problem. Okay, so I'm gonna stop sharing screen unless you have any question for me, folks. Anything?
Dr. Wu,
Yeah.
are you gonna be on campus at all this week?
No, unfortunately not. I'm right now. Before I do that, let me stop recording so I can do this thing. Oh, where's that?